Hello, and welcome to Aggressive Physics. Today is day 28, and what I'd like to do today is solve some problems dealing with projectile motions at an angle. And what I decided to do is choose 4 different types of problems that you may find. These types of problems are traditionally the ones that will be asked dealing with different ways to solve projectile motions at an angle. We'll deal with problems where they land at the same height, problems where they land higher than they were launched, problems where they land lower than they launched, and then even look at a problem where possibly we throw an object downward through the air. A lot of times we deal with objects moving upward first in a specific problem. Now, however, we may deal with projectiles where we want the projectile to move downward initially in order to land at a specific spot on a court. For example, if you're playing tennis, what you're going to do when you serve is throw the ball up in the air vertically and then strike the ball in a downward direction so that you get it over the net into the service box. And in that case, you'll have an initial velocity that's downward. So that means that the VIY is going to have a negative value to begin with. Now, mathematically, that will work out the same as any other problem, but it's something that we haven't talked about before, and I want you to be aware of the different types of problems. Now remember, we're going to do 4 problems together, and these are not every different scenario that you can possibly be asked to solve. These are 4 typical problems, 4 problems that can and have come up before in past assessments, and I want you to be aware of the 4 major types of problems. On the Regents exam, on an assessment, on a homework assignment, you could be asked to solve any different problem. And what's important for you to remember is that we have dealt with different problems in the past. You are working on your problem-solving skills. And the only way to get better at this is by practice. We'll do 4 problems together, but it's important that you do your homework assignments, your classwork assignments, and other quiz and tests that you may have in order to get better at this. The more problems you do, the more repetitive you are, the easier the problems will be in the future. So as far as today goes, I think we're going to have a work day where we're going to solve 4 problems together. Now let's get on to it. All right, we're going to look at 4 different types of problems you can deal with projectiles, and this first one is a standard problem with an angle. We have a football player kicking a ball at 12 meters per second at 33 degrees. You want to find the range of the ball, which is the distance it moves downfield. Now, of course, like any angle projectile problem, you're going to take that angle and you're going to get a little angry and you're going to break some legs. So V cosine theta will get us our x, V sine theta will get us our y. So 12 times the cosine of 33 gets me 10.064 meters per second. And 12 times the sine of 33 gets me 6.54 meters per second. All right, those become our x and y givens for the velocity. Vx is 10.064, Vy 6.54, Ax still 0, Ay still negative 9.8, dx is what we're looking for, and dy is 0, lands at the same height. So in the y direction, where I know more information, I'll find time, and I'll substitute that into the x direction. So for the y, d equals vit plus 1/2 at squared. 0 equals 6.54 times t plus 1/2 negative 9.8 t squared. Factor of t, 6.54 minus 4.9t. Those all equal 0. So my 2 roots, t equals 0, and t equals, we'll bring the 6.54 over, and divide it by 4.9. We'll get 1.33 seconds. And the 1.33 is the one we're going to use. So 1.33 seconds here. dx vixt 1/2 axt squared. The a term cancels. And we're left with dx equals 10.064 meters per second times 1.33 seconds. 10.064 times second answer, and we have 13.43 meters. So the ball lands 13.43 meters downfield. Same height that it landed on, so the key to this problem is that dy is 0, and then we're able to factor out the t and solve for two t terms. All right, now we happen to be on the rugby pitch, and we're striking a ball over the goalpost. Now, the ball has a speed of 17 meters per second, and we're kicking it at 50 degrees. We want to find out how far away the person can be from the goal if it's going to barely skim the crossbar 3 meters high. So we're kicking it from the ground 3 meters into the air. Now, that being said, as soon as there's an angle involved, what I'm going to want to do is our standard procedure for dealing with angles. We have 17 and we have 50 degrees. So V cosine theta for the x, V sine theta for the y. And let's see what we get when we multiply 17 times the cosine of 50. We end up with 10.93 meters per second. And if we do 17 times the sine of 50, we should get 13.02 meters per second. All right, so then what we do in this case, as we've done before, we set up our givens list. We have our x and we have our y. And what we'll do is we'll start with v in the x, which is 10.93, v in the y, which is 13.02, a is 0, a is negative 9.8 for the x and y. At this point, we want to find dx. We don't know what it is, so I'm going to put question mark. And then dy is positive 3 meters because it moves upward 3 meters from where it started. All right, so we're going to solve for t and plug it back in and figure out our displacement in the x direction. Now, this looks like it's going to involve a quadratic. D equals VIT plus 1/2 AT squared. 3 meters equals, and this is the y direction first, 13.02 meters per second times t plus 1/2 minus 9.8 meters per second squared t squared. And what we're going to do is simplify this. So it's going to be minus 4.9 t squared plus 13.02 t. And then we'll bring the 3 over. Minus 3 equals 0. Now at this point, we're going to need to use a quadratic solver. And we're going to get 2 roots for the time. All right, using the quadratic solver, I'm going to get t to be 0.255 seconds and t to be 2.402 seconds. Now the question asks, how far can the player stand from the 3-meter high goalpost if the ball barely skims the crossbar? Now I'm assuming this means the farthest distance total. So I'm going to use the bigger time in this case. Now if we remember, there's 2 times where the rugby ball in this case will reach the goalpost. So if this is the goalpost over here, we'll hit the goalpost at these two locations, and that's what these times represent. 0.255 seconds after it was kicked and 2.4 seconds after it was kicked. And to get the farthest distance, we'll use the farther one, the bigger one, because it'll be on its way down. So that means when I plug my t in, I'm going to do 2.402 seconds. Now, before we did the soccer problem, where we calculated both, and those were the two spots they could have been located, and it wasn't as clear. This one is the farthest, is what the question asks. So now I'm going to use the x direction, and what I'll do is I'll say d equals VIT plus 1/2 AT squared. D is what I'm looking for, 10.93 times 2.402. I'll take 10.93 and I'll multiply it by 2.402, and I'll get 26.254 meters. So the person can strike the rugby ball 26.254 meters away and barely skim the crossbar 3 meters high. All right, in this problem, what we're going to look at is a baseball player who obviously has something wrong with his arm because it's got some kind of Gumby disease here. Maybe he's got two arms, kind of like an octopus or something. However, with that said, he's throwing the ball downward. So he's pitching. I don't have the ability to draw a baseball player pitching. Most of my people do look identical in nature. Now, that being said, 22 meters per second is the way I'm throwing the ball. In this case, it's with a 10-degree angle down. So instead of drawing my right triangle upward, I have the hypotenuse pointing to the downward direction. That doesn't affect the sine and cosine because the 10 degrees is still touching the adjacent here, which is the x-axis, which means I'm going to use cosine for the x, and I'm going to use sine for the y because it's opposite the 10 degrees. However, that's going to make this y component a negative value, and that will change how the roots are formed when we do our quadratic in a little bit. Now, since we've done this process many times, 22 times the cosine of 10 will get me a root of, so the x root will be 21.666 meters per second. And the y root is going to be 22 times the sine of 10, or 3.82 meters per second. And it's very easy to forget about this little negative sign. We've often worried about the signs for the displacements. That's been a standard. We've worried about the sign for the acceleration because acceleration of gravity is always downward. But we often have objects being thrown upward. So in this case, throwing it downward, the main change is that when we do our Vx and Vy, the V and the x is still 21.666, and the Vy becomes negative 3.82. And if we forget that, it's going to change the answer. In fact, when I typed it into my quadratic solver, I forgot to use the negative as well. And what ended up happening is if you forget the negative and then you add the negative for that b term, you'll actually switch which root is negative. So when we get to that, I'll explain a little more in a little more detail. Now, I just glossed over the accelerations. Of course, the x acceleration is 0. The y acceleration is still negative 9.8. And d in the x direction is what we're looking for. dy is negative 1.8 meters because the ball falls downward. Well, like every other projectile motion problem, we're going to solve for t in the direction we know the most about, and then we're going to use that in the other direction. And we know the most about the y direction. So let's solve for y. D equals VIT plus 1/2 AT squared. And negative 1.8 meters equals negative 3.82 meters per second t plus 1/2 negative 9.8 meters per second squared t squared. And I'll simplify that by doing negative 4.9 t squared minus 3.82 t. And I think I forgot to write the t in the equation. And then if I bring the 1.8 over, it becomes positive 1.8 equals 0. So my a term is negative 4.9, my b term is negative 3.82, and my c term is positive 1.8. And I'm going to get two roots. And the first root will be negative 1.11, and these are seconds, positive 0.331 seconds. Now, of course, I want to use the positive 0.331. So when I go to the x direction, d equals vit plus 1/2 at squared. The a term cancels, and we're left with d equals 21.666 meters per second times 0.331 seconds. So I go back to 21.666 times 0.331. And when I multiply that, I'm getting 7.2 meters. I got 7.171, but I'll just round that to 7.2 meters. And depending upon if this were part 1, there would be multiple choices, and the precision would be defined by the answers of the problem. Now, in this case, octopus baseball player throws the ball downward. This negative sign here is the key. When I did this incorrectly on the quadratic solver, which I did beforehand, it actually switched the terms. The positive term was the 1.11, the negative term was the 0.331, and that would have radically altered my answer. In fact, instead of throwing 7 meters, we would have thrown it over 22 meters, which is quite a big difference. So that is how we deal with a problem where the initial velocity is negative in the y direction. We just use the negative sign in the equations because they're vector equations. Handle it easily, and as long as you plug in the proper signs, the answer should be correct. All right, our final projectile motion problem deals with a field hockey player. And I was a little embarrassed by my baseball player's arms, so I really brought out the A game here to draw my field hockey stick. And I find this to be one of my finer drawings, well, maybe ever. In this case, what we're doing is we're striking a field hockey ball, and it's going at an angle of 10 degrees, and it's flying through the air and landing on the ground. And we know it goes 15 meters, but we don't know how fast it was struck. And this is one of those problems that seems to come up every year in class, and students become paralyzed. They get, the shivers, they break into a cold sweat, and they rarely make it as far as they rarely make it anywhere past this point right here. They might be able to draw the diagram. They have the 15 meters here. They draw the triangle, and then they just panic. And that's because usually we have a value for this v. And in this case, we don't. It's our unknown. But remember, no matter what, you can still break the legs of a vector. You can resolve it into its components by using sine and cosine. And every time I've started the problem where we've broken legs, I think we've started with this v cosine and v sine. But we've known the numbers to plug in. So we've had 15 and 20 and 30 and 55 and whatever the number happened to be. Now in this case, we don't. So this becomes one of our unknowns. In fact, it becomes the key unknown because it's our ultimate goal. And we cannot find the legs, and that makes people uncomfortable. Anytime we have two unknowns, that brings a level of discomfort to the table. So what we're going to do, and the key to solving this, is really just a matter of plugging in what you do know. Now I want to find Vx. Well, it's V cosine 10. And I want to find Vy. Well, it's V sine 10. And I don't know a number, but I'm going to have to be okay with that. Ax, well, do we know what that is? Sure, still 0. We're not doing this in a windy environment. There's no fans on the field. Fans that blow air, not fans. Hopefully there's a lot of fans on the field cheering on the team. The AY is negative 9.8. Regardless of the fan situation, gravity will still be there. If the players were by themselves on the field, there would still be a gravitational pull downward. Gravity's dragging you down whether or not you're with a lot of people or you're by yourself. Gravity, for some of us, may be our only companion. We may be alone often, but gravity's always there by our side. Now, the 15 meters is my x, and maybe our hidden variable that would be another stumbling block would be the fact that it lands back on the ground. And I know I drew this, so it was kind of in the ground. I guess it was struck pretty hard. It actually embedded itself in the ground. And you get dy to be 0. So that's going to be our, I guess, second hidden variable. But zeros are easy to deal with mathematically. Now, as always, we're going to try to find the time, plug the time into the other direction, and solve for, usually we solve for dx, but what we're going to need to find in this case is v. Now, if you look at our givens list, we have a v and we have a t. We have a v and we have a t. We have a couple of zeros, which are always good when you're solving problems because they'll simplify. And we have a 15 and a negative 9.8. And what I'm going to do is just write our equations as we always would. D equals VIT plus 1/2 AT squared. And we'll start in the y direction just because that's usually where we start. 0 equals v sine 10t, two unknowns in that term, plus 1/2 negative 9.8 meters per second squared times t squared. So we don't know v, we don't know t, and of course we don't know t squared. And let me do the same. You know what? I'll simplify it. 0 equals v sine 10t minus 4.9 t squared. So here is one equation. And we'll do the same for the x. d equals vit plus 1/2 at squared. d in the x is 15 equals v cos 10 times t. Two unknowns in that term. And fortunately, this 1/2 at squared is going to cancel. Now, this is our second equation. And what I often fear is substituting in for anything that's squared. So what I'm going to try to do is I'm looking at solving for the v, and I'm going to replace this v right here. So I'm going to take this and get that by itself. And the way I would do that is I would say, if I just do it over here, I'd have v equals 15, and I'm going to divide cosine 10 t over to the other side. So this equation here, I'm just going to circle it, is the simplified version of equation x that has v by itself. Now I'm going to take this term, what v stands for, and I'm going to plug it in now to equation y. So substitute v into equation y. And let's see what we get. 0 equals, all right, here's our substitution, 15 over cosine 10t. So this whole term is then multiplied by sine 10t and minus 4.9 t squared. Well, if we look at this, 0 equals 15 sine 10t over cosine 10t. Well, what do we know about sine and cosine? If we divide the two, we should end up with 15 tangent of 10, and these t's will cancel out. Minus 4.9 t squared. Well, look at this. One unknown, and it's t. So what I'm going to do is bring this 15 over, 15 tangent 10, now 15 times tangent 10 is a number, it's 2.645. And I'm going to bring it over and divide by 4.9. And since I'll bring it over and it'll be negative, that will be countered with the negative of the 4.9, and t squared is 0.54. So t squared equals 0.54 seconds. Take the square root. So second square root, second answer, you get t to be 0.735 seconds. Well, that is the time. And if we take that time and we substitute it in right here, v is going to be an answer. And it's going to be 15 divided by parentheses cosine 10 close parentheses times 0.7345. Well, that's still in my calculator. Second answer, I'll close the big parentheses and I'll hit equal. And when you do that, you get 20.73 meters per second. So from this extremely complex problem with very little given information, we just plodded along. Slow and steady won the race. We were able to plug in what we knew, got a little closer. We had two equations, two unknowns, substituted one into the other, and that simplified so that we were able to solve for t and then ultimately solve for v. Now, of course, this isn't a problem that you'd see every day, but I want my students to realize that even problems that appear impossible at first are feasible. And you have the skills now to solve problems that range in complexity to, three variables, v equals d over t, all the way to projectiles flying through the air and landing at a specific spot with an unknown velocity. So this is our final projectile motion practice problem. It is the most difficult that we've looked at, I think, thus far. And we'll move on to vectors in the next chapter. Make sure you do some more practice problems. Make sure that you can do these problems on your own. And the more practice problems you do, the better off you're going to be. Because, as always, I make this look easy. But more importantly, I make it look good.